Hi everyone, welcome to day 3 of my cloud computing series. So, today we are going to learn these topics. First, context switching in operating system. Second, what is convey effect. Third, shortest job first algorithm. Third, multi level queue. And fourth, and fifth is what is concurrency. So, now I'm going to my notes where I'm going to explain these topics. So context switching means like we are discussing in previous videos also. So what is context switching is means like we have learned that PCB, uh, process control block. So we here like P1 and P2, they are storing this PID. I have explained you before previous lecture video this, so I'm not going to explain again. So what P1 and P2, so through this context switching is happening. Okay, so if you see like P1 and P2 is allocated to CPU, this CPU based on their you can say if time sharing is happening or P1 going for some IO and all. So what will happen, there is like overhead happening because P1 is like going for IO or software interrupts has come because of time sharing. So what will happen, P2 has allocate to the CPU. So what will happen, CPU is doing context switching. So because of this pure head is occurring. So this is the pure head. So now I'm going to explain orphan process. Orphan process, what is orphan process basically means, like P1 is running something, and it's like it has a P2 like child, has child, but after that sometimes P2 has exit or terminated or exit. So what will happen now, this child P2 has no parent. So in that case what OS is like smart. So OS will what OS will do, OS allowed this in int to be as a parent process to this child. So for this it's like a operand process, it's called operand process. And what is this zombie process? So like if parent is having child process, and parents waiting for like 5 minutes, but this child process executed and it's executed in 1 or 2 minutes only, this process, and this process exit. So this parent have waiting for 5 minutes, so it's like P2 has executed in 2 minutes. So parents does not know that P2 has executed and all. They are waiting for 3 minutes. So this 3 minutes is called zombie process because it's taking space and resources of that CPU. That's why this call is zombie process. So what is process scheduling? If you see, process scheduling means like ready to queue to allocate the CPU, that is called process scheduling. Okay, so we are going to now explain how the process scheduling is happening, like this P1, P2, P3, how this allocated CPU, how allocated to this P1 and P2. So we are going to understand by this. So firstly there is a non-primitive scheduling. So in this what is happening, if P1 is allocated to CPU1, then P2, P3 have to wait until this P1 has completed or terminated, then P2 will allocated the CPU. So in this time sharing is not happening, starvation is happening. So non-primitive is not good. And in primitive scheduling, what will happen, P1 is allocated, but there is a time sharing. If this time sharing is there, then it will be and in this case what will happen, P2 allocate to CPU like that. So there is like if you can see starvation in like in non-primitive, starvation is like more. In primitive there is low chances. CPU utilization is more in primitive because P2 having time sharing and all, and it's allocated based on that. So what will happen? Primitive has more CPU utilization, better than non-primitive. That's why I have written it is increase and it is decrease like this. And overhead in primitive is more because if you see, if P2 is have time sharing has it happening, so what will happening, P2 will allocate to this, but 1 second of 2 second has to go IO or some software interrupt of time sharing has completed, like 10 second has completed, then he has to go to the again ready queue. So what will happen then, P3 will allocate. So in this primitive, uh, overhead is more, uh, and non-primitive has like a low. And now if some what is the goal, like if you are creating some operating system, so what will be the what will the process of that goal of that CPU or operating system. So here we are discussing goal of CPU scheduling, like how you scheduling your CPU to the that process and all. So we are like this goals. So we are going to compare that process, like that algorithm through this uh, goals. Okay, first is maximum CPU utilization, it is most and it is like mean. After that, minimum turn around time. What is turn around time means, like जब भी जॉब रेडी क्यू में आएगा और टर्मिनेशन का टाइम उसको बोलते हैं टर्न. लाइक इफ you see, in process has come this in ready queue, and after that this have like scheduling and this like waiting and all, after that happening, after exiting that process, this whole time what is take, it's called as turnaround time. Okay, so basically it's like that, like we have discussed what is minimum turnaround time will there, minimum wait time will be there, like waiting time is not more, so this is also must. Fourth, minimum response time. If P1 has come to this ready queue, then P1 and P2 has come this ready queue, then P2 when he come, like P1 has now come to in red, P1 has come to this ready queue, then only the CPU allocated to this P1, then this will response time is minimum. So that will be a good operating CPU scheduling, so this will be a good thing. Okay, and the maximum throughput, like ज़्यादा per unit process करे, like how many maximum you process unit per second, like that it's saying that. Okay, so we are now discussing for algorithm now. So first is FCFS. So what is first come first serve? So what will happen if P1 has come, then it's selected first and dispatched to CPU, like allocated CPU to P1. Then what will happen? Uh, it allocate to that whichever processes will come first will allocate that PC. So in that there is a problem, conway effect. What is conway effect we are going to discuss, like this P1 has more burst time and more burst time. So what will happen, if you see this example, there is P1, P2, P3. Okay, and arrival time means when in when when the process arrive in the ready queue, that will that call is around arrival time. And what is burst time? Burst time means like we are assuming that this process will take this much time to complete that process and exit, that will call burst time. And what is CT? CT like have like CT means like waiting something, and T T80 means like turnaround time. I have explained you what is turnaround time, and waiting time I have also explained. So in this example we are going to now explain, I'm going to explain this P1, P2, 3, and there is arrival time and there is burst time. So first we have to like calculate their uh, uh, like Gantt chart. This is Gantt chart. Okay, CT is Gantt chart. So what will happen? How much time it will take? So when P1 has come and bus time is 20, P1 take 20 time, 20 seconds. After then P2 has come, so P2 has take 2 seconds. So what will happen? 20 plus 2 is equals to 22. After P3 has come, it also take 2 seconds. So what will happen? 22 plus 2 will 24. This Gantt chart will be showing this like this. So in this we are going to calculate 20, 22, 24. Okay, so now what will happen? If for turnaround time we have to calculate, so what we have CT minus 80. So CT minus 80, to 20 minus 0, 20, 22 minus 1, 21, 24 minus 2, 22. So this turnover time has come of this process P1, P2, P3. Okay, so now we are going to like calculating wait time. So for calculating wait time, there is a turnover time minus BT. So turnover time is what? 20 minus 20, it's equals to 0. 21 minus 2, what will? 19. And 22 minus 2, what will? 20. So the average of this so when we are getting is 13. So in this, if this is the example where I have explained. Now I'm going to explain what is convey effect. Suppose if you take P1 as a last burst, or this is the largest burst. In this, what is happening? Now first I will explain this, then I'm going to explain what is convey effect. Okay, in this we are uh, like based on their low burst time, we are arranging process. So this is low burst time 2 to 20. So this is P2, P3, P1. Okay, so what will happen? We have taken their CT, you can calculate by through Gantt chart. So this is 2 to 2 4 24. Okay, and turnaround time we have taken, and this is the wait time. If you see, then you will understand this example. Now what is happening? If you add and take their average, take out their average, it will come 1 unit. So what will happen? This, if you see this, if you first take if first process is big, first process the burst time is large, then other process has to wait a long time. So this convey effect basically is this only. So we have to wait of, or if this is the convey effect. But if you take a low burst time, then what will happen? That average time will average unit will be the lowest. So this is the convey effect. If you take first large uh, burst time, then it will be a convey effect, and the other process has to wait along. That is why uh, this is the convey effect. Now we are going to learn second, shortest job first, like SJF. So this is non-primitive process with least burst will be get CPU. Like whoever have least burst timing, they will get that CPU. Basically it's saying like that. So you can see this example carefully. So you can get like P1 has 2 and P2 has 5, P3 has 10. So this is has lowest burst time, so CPU allocate to P1. Basically it's saying like that, and you can calculate through this. Okay, and of primitive shortest job first. So if you can clearly understand that in this it's happening, like whoever has shortest like least burst time will get allocate that CPU. But it's a non-primitive, you know that non-primitive has no time sharing and all. But in primitive there is time sharing, so it is like that. So it is a better version of the primitive of shortcuts. This is the only. Now the second is priority scheduling. Priority scheduling is assigning priority to each job. Like we are assigning each process to priority like that. So if you see the P1, P2, P3, this is the process, and this is we have given the priority, and we are going to calculate. So what is the arrival time and burst time and CT? You can take out CT through Gantt chart, and turnaround time and waiting time. Okay, so if you see priority in this, who is the lowest, this is 2, so it has allocated first, and you can take this first time, and if you calculate, this is average we will get. This is the non-primitive. If you see, non-primitive have no time sharing, but if you this same priority algorithm we are applying in primitive, so we have a time sharing also. So it will be like we have 0 or 1 priority, so it will have it run for 1 second. After that, this like this I have a 5, okay, let example this has a 5 priority or 3 priority, but and this process has not come yet, okay, in ready queue. So what will this process allocated the CPU, CPU allocated this process, and it run 1 second only, then this process has come. So this is the priority 3, but this is the 2, so this is the minimum. So what happened, then it this process will go to again ready queue, and this will run the CPU allocated to this CPU. So because of the time sharing and the priority based on this big word, that's why. Okay, so this is the, but is the big problem of this is uh, if you have like large priority, then it will happen infinite waiting. So if you, there is a rumor also, I can not say that is right or true or wrong, but in IBM in 70994 at MIT, on they on submit on job this date, job submit on some days, process from some so on days. Then in 1973 they check the lowest units are uh, there only. They have never allocate the CPU. So this is the big problem. So the solution for this, to avoid infinite waiting, the aging has come to the picture. What will happen if this after every 50 second, if the lowest priority has, like lowest priority has, so it will be at one, like at plus one, that will and I have explained you like uh, very well. So it's if this has lowest priority like 2, so what will happen after so many like every 50 second it will be plus 1, then it will be 3, after 50 second it will be plus 1. So in this what will happen, this not going to be in infinite wait. So this aging has come and it solved this problem. Now we are going to learn third, round robin, RR, basically is short from RR. So it's lowest starvation, most popular algorithm. It's a primitive version of first come first serve. So criteria is time sharing happening in this, because you can see. So this is the example, easy to implement. Okay, P1, P2, P3, you can see this example. Okay, now we are going to learn multi level queue scheduling. So what is before we are just only applying the process and all, but what we are going to do, we are going to first divide this into three. Like if system process created by OS, interactive process, like we are dividing the process based on the this three. So if you see system process created by operating system, whichever operating system is running their process, it will be running this an interactive process, whichever user has give their like a process, it will be run this interactive process and batch process. No user, it run only background like input and output. This process it running in this batch process. So we basically have divided this three. So based on this is the higher priority, after that interactive, after that, so for like this is the highest, after that this, after that, so it is lowest priority. Okay, if you see this is also having a issue, because if you see there is a, it is has lowest priority, so batch process will not getting process like that. It has to wait and it could be indefinite. So in like multi-level we can't do anything. But this and this is not right now, this all algorithm running in the old devices. Right now this multi-level feedback queue scheduling running in nowadays operating system. Okay, so what will happen, there is a multi sub queue that three I have explained, like these three uh, operating system process, interactive process, and batch process. These three, and if you see, you can't interact because we have divided, so that process can't interactive or can't change in in this. But in multi-level we can change the process, we can add burst plus. So what will happen if interactive queue movement is allowed? So this batch process is having low something, but after some time it will like having edge also in that. So what will happen, it will go to that interactive process. So it is like that. So you can interactive in that sub queue also. So separates process based on that. Lower queue aging method, lower process like aging method is also in this. Because of this it is has a best. Okay, now we are going to learn concurrency. What is concurrency? Means multiple instruction at the same times. Okay, so the process, this is the process, and t1 t2, and this is the threads. If you see threads. Okay, so what will happen if I can say threads only work in a multi cpu only, that will be the best. Like that will be the best. Okay, so this is the thread. It's using one address space, and in this context switching is very fast and everything very fast. So based on that it is had. And thread also have tcb, thread control block. So this is like that. If you see their structure, so stack we are storing static data and all, and heap data and text, the whatever we have. So I think I have explained you very well, so you can see. So basically I'm explaining short, because I have explained you, no one have that much time to see 1 hour video or 13 hour 13 minutes of video. So that's why I'm making video only 25 or 30. So I am going to just going to overview what I have learned, so you can getting what my notes and all. So I hope you will guys understand. So thank you everyone. We will going to meet tomorrow with new topics. Bye.